Good afternoon, everybody. I'm Andrei Tokmakov, Chair of the Department of Chemistry here at the University of Chicago. I'd like to welcome you to the fourth series of presentations we've had this fall by scientists whose research addresses a host of related interdisciplinary questions regarding the origin of life, from planet formation to chemical reactivity of life's precursor molecules. For those of you that have not been able to see all of the presentations, I do want to remind you that these are recorded and you can go back and view some of the older ones. You can access those from our website. Today, it's a pleasure to introduce Dr. Jenny Bergner. She is the NASA Hubble Postdoctoral Fellow in the Department of Geophysical Sciences here at the University of Chicago. Jenny's research covers the chemistry involved in the very earliest stage of planet formation in protoplanetary disks. And her tool set covers all sorts of methods, all sorts of techniques. And that includes extensive observations of interstellar clouds, laboratory studies of chemical reactivity, and then accompanying theoretical studies, really all to try and describe chemical evolutions in those systems. So with that, I'm going to turn this over to Jenny so that we can hear from her about astronomical insights on the delivery of organic building blocks to new worlds. But 1 second, I'll just also remind the audience that you're welcome to send some questions in for us to discuss at the end. Please enter those in the Q&A box at the bottom of your screen. So thanks, Jenny, floor is yours.
Great, thank you, Andre. Thanks so much for the opportunity to talk here and share my research and sort of what's going on in my field as a whole. So, oops, wrong one. Sorry. Screen sharing challenges. Are you seeing the presenter view or the other view?
It's the right view.
Okay. Okay, so you're not seeing
no, it's good.
Okay, great, cool. This is different. Okay, sorry for that. So yeah, I'm gonna be sharing what we can learn from an astronomy perspective on how these organic building blocks are delivered to new worlds. So one of the really exciting possibilities opened up by studying planets and other star systems is that we might be able to ultimately increase our sample size of what a habitable planet might look like. So it's kind of broadening our perspective of origins of life chemistry to a more universal view. And what I'm showing here is an artist's conception of nearby known exoplanets that are classified as potentially habitable. So it can be really fun to think about these nearby habitable planet candidates as potential laboratories for us to someday in the future study origins of life in a more kind of broad, holistic way. But we're still in the very kind of early days of characterizing the physical and chemical properties of other planets. So in this ranking, habitability is just defined as planets that are likely to be rocky and to maintain a surface liquid water. But as many of us in the audience know, having a rocky surface and water isn't fully sufficient for sparking life. There's a lot more that goes into it. So here on Earth, we know that there's a vast diversity of different life forms. But underlying that diversity is a handful of what we call bioessential elements. So carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. And these common elements are shared by all life forms. So they're really the kind of fundamental drivers of organic biochemistry. So we want to understand both how Earth was seeded with these elements and also whether these exoplanet kind of Earth candidates, in addition to being rocky and temperate, also inherited these ingredients for origins of life chemistry. So we're not at a stage yet with exoplanet studies where we can actually answer these questions. We cannot currently characterize very well the atmospheres of rocky planets, and so we're not really learning much about the volatile chemical inventories of these planets. And looking forward, the prospects aren't good for a few decades at least. So in the coming few years, we may be able to sort of do these atmospheric retrievals for a few exoplanets, but it's not until the 2040s at least that we're actually going to be doing this on a meaningful scale. And that's with the launch of these future kind of mission concepts that are being considered by NASA. So in the meantime, we're sort of left with this knowledge that there may be numerous Earth cousins in other star systems, but we don't really have good constraints on this aspect of chemical habitability. How likely are they to kind of inherit the ingredients that you would need for a subsequent prebiotic chemistry to take place? So how else can we get at this question of chemical habitability if we can't characterize the inventories on these planets directly? So instead, we can study the compositions of the progenitors and try to understand what the chemical initial conditions are for planet formation. And by doing this, to learn something about the inventory of these biogenic elements in other planetary systems. So here I'm showing sort of the formation sequence of how you would form a planetary system. And this is actually just a very common outcome of the formation of low mass stars like our own sun. So we begin with a molecular cloud, which is just a sort of dense cloud of gas and dust in the interstellar medium. And at some point you have a perturbation that might affect some region of the cloud and cause it to begin to collapse in on itself. This brings us to the protostellar stage. So in this stage, we're actually starting to form our star at the center of the object. And we might form a small accretion disk that's feeding material onto the star. And then we're surrounded by this cloud of gas and dust, which is the protostellar envelope. Later on in the evolutionary sequence, we're left with the protoplanetary disk. So the envelope has dispersed by this stage, and this is just the flattened disk structure that's remaining. So this disk is, again, feeding accretion onto the central star, but it's also historically been considered the site where planet formation is ongoing, because you have high densities of solids in these disks that can aggregate, grow to larger sizes, and really kick off the process of planet formation. And then ultimately, sort of at the end of this process, the disk will disperse as well, and you're left with just this isolated planetary system. So I think ultimately it's quite likely that these planetary compositions that we're left with in the end are going to be set by some combination of inheritance of material from these earlier stages of interstellar chemistry, like the molecular cloud, and then some reprocessing that's going on during the assembly of planets in the disk. And so one of the big kind of questions in my field is trying to disentangle the balance between this inheritance and reprocessing in setting the composition of planetary building blocks. So I want to take a minute to just familiarize everyone with the physical environments in these regions. So in the case of protostars, we have this sort of warm condensation at the center of the cloud that is the forming star. And this leads to a temperature that's increasing as you move closer to the center of the protostar. Like I said, we also have envelope material that's falling in towards the inner region of the protostar. And this is also often accompanied by the presence of a protostellar disk that is feeding material onto the star. Outflows are also a really common feature to see in protostars, which is just material that's being launched away really energetically, kind of opposite direction to the disk. And in both accretion onto the disk and in the case of outflows, we're often accompanied by energetic shocks that are happening when different materials are sort of blasting into one another. So this is the physical picture for a protostellar environment. When it comes to the more evolved disk environment, we have already dispersed our envelope. So in this case, we basically have a disk surface that's just fully exposed to irradiation by the central star. So you have a lot of UV and X-rays that are impinging on the surface of the disk. So our temperature gradients in this case are increasing, moving radially towards the star, and also increasing, moving away from the midplane in the disk. This gives us these three kind of characteristic chemical regimes that we like to think about. So they're pretty much set by the level of radiation that is penetrating in the different vertical layers. So this top layer, the photon-dominated layer, this is basically just being blasted by radiation. It's really difficult for molecules to actually survive in this layer. But a little deeper down in this warm molecular layer, we have more shielding, and so it's actually quite hospitable to the formation of molecules. And then deeper still, most of the radiation is not penetrating to these depths. And so the temperatures are really low, and you end up actually freezing a lot of your molecules out of the gas phase and onto the surfaces of dust grains. So in addition to these distinct chemical regimes, we also know that there's sort of robust dynamical processes going on in the disk that can redistribute material both radially and vertically. So we might have mixing, settling, and drift that can also move material around between these different regimes. So an important thing to highlight, for those of you who aren't used to thinking about planet formation, is that the planet formation process is going on in this dense frozen midplane layer where you have a lot of solids around that are able to stick together. Most of the observations that I'm going to be talking about are actually probing this warm molecular layer. So I just want people to appreciate that there's a bit of a mismatch between what we're actually able to probe observationally and then the actual site of planet formation. So now that we have an understanding of these physical environments, let's think about what types of chemistry can actually proceed. So the chemistry in these star-forming environments is pretty exotic, actually. We have very low temperatures and low densities, and this sets a couple of strict criteria for what kinds of chemistry can actually take place. So we know that reactions have to be exothermic and barrierless because of the low temperatures, and they have to occur when two bodies are colliding because you don't have usually high enough densities for three body processes to take place. So in the gas phase, the most effective kind of chemistry is reactions between ions and neutral molecules. And this leads to the buildup of these really exotic species, like these unsaturated hydrocarbon chains that you would never see really on a terrestrial environment. The other alternative for how chemistry can proceed is through grain surface chemistry. So dust particles account for a really small percent of mass in the interstellar medium, just about 1%, but they play this really outsized role in regulating the chemistry. And this is because in these cold, dense regions, a lot of the volatile molecules will freeze out onto these dust grain surfaces. And this will basically do a couple of things that will sort of ease these constraints on the chemistry. So you concentrate your volatile reactants, it acts as a built-in third body, and it can even give you multiple reaction attempts if you have molecules that are just sort of stuck next to one another. So through this grain surface mediated chemistry, we're able to form molecules that look a lot more like what we would find here on Earth. And in particular, molecules that we might find in an organic chemistry lab. So things like methanol or dimethyl ether. So in astronomy, we call these molecules complex organic molecules. And I know probably all the chemists in the audience are laughing because being 6 atoms isn't complex from a terrestrial standpoint. But for astronomy, it is really sort of at the higher end of the size of molecules that we can characterize. So I want to return to the title of my talk, which is to try to understand how organic building blocks are delivered to new worlds. But I want to first sort of unpack what we mean when we're thinking about an organic building block, because there's a few different interpretations. So on the one hand, you could have the idea that these complex molecules themselves are prebiotic building blocks. And that's because you actually find molecules that are either interesting prebiotically themselves, or they might carry a prebiotically interesting bond. So the sort of caveat to this is that you have to deliver the molecule then intact. And we know that to some extent this happens because we see complex organic molecules that are preserved in meteorites that have been delivered to Earth's surface. So we're going to hear a lot more about this next week, but it is sort of not an obvious thing that all of the material that we see in interstellar medium is actually going to survive that journey. But the benefit of this is that you can then sort of seed your young planet with this prefabricated material that could then potentially kind of give you a leg up in jump-starting organic chemistry. On the more pessimistic end of the spectrum, we might have just basically the volatile elements as our organic building blocks. And so you're being a bit more agnostic here about the form that they're actually being delivered in. You basically just want these sort of most essential ingredients to be delivered to the planet. And so we don't really care in this case about the form that they're delivered in as long as it's volatile. And I just want to note that this kind of pessimistic view actually still includes complex molecules because they are generally important carriers of volatile elements. So depending which sort of end of this spectrum you're thinking about, the questions that we want to ask from a delivery standpoint are going to be different. So in the comms as organic building blocks kind of end of the spectrum, we want to understand what biologically relevant molecules can actually be synthesized in the interstellar medium, what conditions are they formed in, and in what abundances, and can they survive the planet formation or later impacts? In the case of the elements as building blocks, we want to understand what the partitioning is of volatile elements among different molecular carriers. We want to understand how physics and chemistry might reshuffle this partitioning along the star formation sequence. And ultimately, we want to know how these different factors are going to impact the elemental ratios that are ultimately incorporated into planetesimals. So these are just sort of the two different views. In my opinion, both of them are informative because we don't yet really understand how life started on Earth. So it's important to keep our options open. So the survival question in the case of comms as building blocks is definitely difficult to quantify. But like I said, I think we're still learning something by studying both of these angles. Okay, so how do we actually study chemistry in these planetary system progenitors? A lot of the work that I'm going to be talking about today is using radio astronomy. So this is telescopes in the sort of sub-millimeter to centimeter wavelength range. And with these wavelengths, we're sensitive to transitions between the rotational levels of gas phase molecules. So this lets us characterize the gas phase molecular content of material in these objects. But we're also sensitive to thermal emission from dust grains that are sort of on par with the size of the wavelength that we're observing at. So we can also get some constraints on the distribution of millimeter to centimeter size grains in these objects. And in particular, I want to highlight that our ability to characterize chemistry in these star forming regions has really been revolutionized in the past 2 years thanks to the ALMA interferometer. So ALMA is an array of telescope antenna that's distributed across the high desert in Chile. And this basically acts as one giant effective telescope disk that's kilometers in size by distributing these antennae over a very large baseline. So as a result of this, we have really spectacular sensitivity and spatial resolution that we can achieve with ALMA. And so to illustrate this is kind of a common trope to show in a talk that is glorifying ALMA, but we like to show sort of the before and after picture. So this is an image of the dust grains in this nearby disk HL Tau circa 2011. And we see that from this image, we have sort of a bright inner region of the disk, but then it sort of smoothly just decreases moving out with radius. And when ALMA came along and took an image, we saw that this is certainly not a smooth brightness profile of the disk. We see instead this really dramatic structure of these bright rings and sort of empty gaps in the dust emission. So you can sort of see how these new observing capabilities are really transforming the way that we can see these regions where stars and planets are forming. From a chemicals perspective, besides just providing us with very beautiful pictures, this has also kind of really been technically a great advance as well. So I want to give an example of the case of how we convert from line fluxes that we observe to actually physically meaningful quantities like a molecular column density or an abundance. So in order to make this conversion, we have to make some assumptions about the emission temperature that the molecule is emitting at, and also the line optical depth, which is a property that can, in some cases, basically saturate the emission that you're looking at and break down a proportionality between the line flux and the column density. So our ability to actually make these conversions has really improved thanks to the higher spatial resolution that we have with these newer generation interferometers. As an example, this is an image of the C2H n equals 2 transition. So it's actually a hyperfine complex. The rotational levels are split into these distinct lines. And so if you were to integrate the emission across this entire disk, you would end up with a spectrum that looks like this, which is in principle 4 independent lines, but they're totally smeared together. And the reason is that the material is moving at different velocities in this disk. And so when you look at the flux sort of summed over the entire disk, you're basically smearing the location of the lines based on the different velocities that the material is moving at. So it's really difficult to fit any sort of predictive model to a spectrum that looks like this. But when we have higher spatial resolution, we can isolate material coming from a smaller spatial scale on the sky. This has less of this sort of velocity spread of the material that we're looking at. And as a result, we get these really nicely resolved line peaks that allow us to actually fit just sort of a standard Gaussian model to the emission. And in this way, we can actually really improve our constraints on the number of molecules that are emitting. So one of the big improvements that we've seen in recent years, sort of thanks to ALMA coming online, is the ability to detect larger molecules in disks. And this gives us a much more holistic view of the chemistry that's actually going on in disks. So to illustrate this, let's consider the history of observing nitriles in disks. For any astronomers out there, a nitrile is just a molecule with a carbon-nitrogen triple bond. And so as far back as 1997, we were able to detect the emission of simple nitriles in protoplanetary disks. So here we're looking at spectra of CN and HCN in a disk, but these are unresolved observations. So instead of having a nice map, like I just showed you before, we basically just have a single spectrum for the entire disk. Then sort of a decade or so later, we were able to actually map the emission of these more simple nitrile species on the sky. So here again, we're looking at HCN and CN, but instead of just a single spectrum, we get now this nice image of the emission. Around the same time, we were able to measure the emission of more complex nitrile-bearing species in disks, but again, in a spatially unresolved way. So this is cyanoacetylene. Again, we have a single spectrum for the whole disk. And then since ALMA has come online, we have actually been able to resolve the emission of these more complex nitrile species in disks. So here is methyl cyanide. This was the first detection in a protoplanetary disk. So because this is so recent of a capability, we're only beginning to really explore questions like what role do these more complex species play as volatile reservoirs within the disk? Are they inherited from the protostellar stage, or are they actually formed in situ in the disk? And how similar is this organic chemistry in other disks compared to our own solar nebula? So until recently, this one detection of these complex molecules in a disk was the only detection that we had. And so expanding the sample size was a high priority in order to actually address some of these questions. So we had a study in 2018 where we performed the first survey looking for complex nitrile species. We targeted 6 disks, and sort of jumping straight into the detections, we found this methyl cyanide molecule in firm detections in 3 of the 6 disks, and then additionally tentative detections in these 2 additional disks. And cyanoacetylene, we were seeing firm detections in 5 of the 6 disks highlighted here. So just to say that now that we actually have the sensitivity to look for these more complex molecules, we find that they're actually quite common. We can also go a bit more quantitative than that and actually figure out how important they are as carriers of the nitrile bond to place some constraints on sort of the role of complex species relative to simpler organics. So to do this, we had 2 disks that had especially bright emission, and we could do what's called an abundance retrieval, where we basically set up a physical model of the disk that describes the temperature and density as a function of position in the disk. And this is informed by literature constraints. So we just fix this physical structure of the disk. And then we can fit just a parametric abundance profile that describes the abundance of the molecules as a function of radius in the disk. And when we do a fitting scheme like this, we here I'm showing the observations on the top row compared to the model that we have generated in the middle row. And you can see that we're doing a really good job of capturing the emission pattern that we're observing in the disks. So the abundance profiles that we pull out look like this. The y-axis is showing the abundance of the complex nitriles relative to HCN, which is our kind of benchmark simple nitrile species. And what we find is that in the inner 100 AU of the disk, methylcyanide is about 1 to 10% with respect to the HCN abundance. And cyanoacetylene is in some cases low, but in some cases as abundant as HCN in this sort of inner disk region. So what this is telling us is that these complex nitrile species are actually important volatile carriers. They can be as abundant as the more simple species. And so if we're interested in characterizing the partitioning of elements among different carriers, we really need to consider these larger species in addition to the simpler ones. Okay, so what about the oxygen chemistry? Methanol is sort of our analog to methylcyanide in terms of being complex organic on the sort of oxygen side of things. So when we look at protostars and prestellar sources, methanol is the most commonly detected complex organic. It shows up almost everywhere that we look for it in these sort of dense regions of gas. But within protoplanetary disks, we've actually had a really hard time finding methanol. It's only been detected towards a single source, and this was done by Catherine Walsh in 2016. So this is not for a lack of trying. There have been a number of deep searches for methanol that have come up with only upper limits for how much methanol is there. So just to sort of put this all together, in one disk, we have a measurement of methanol, and so we can compare the methylcyanide to methanol ratio. And we find that in this disk, the ratio between them is about unity. There are a few other sources where we haven't detected methanol, but we have pretty stringent upper limits on its abundance. And in this case, the methylcyanide to methanol ratio is again consistent with being of order unity. Now, when we look at the other stages along the low mass star formation sequence, we see that something really strange is actually going on in the disk stage. So compared to the preceding stages, we're boosting the nitrogen organic chemistry by something like 2 orders of magnitude. And so again, the volatile chemistry seems to be quite distinct in the disk phase compared to these previous stages of low mass star formation. So it happens that the surprisingly low oxygen content is not unique to methanol. It is also the case for other oxygen-bearing molecules. So in the case of CO, there are really decades of work going into studying this CO emission in disks. And so here I'm showing a nice summary plot done by Coco Zhang in 2020, but this is also building on a lot of other works. So just to recognize that. And so the y-axis is the CO abundance, and the x-axis is showing the age of different sources, with class 01 referring to protostellar sources, and class 2 is our protoplanetary disk sources. So we see that by the class 2 stage, most disks are depleted in CO by 1 to 2 orders of magnitude, and this depletion seems to be taking place sometime around the transition between the protostellar and the protoplanetary disk stage. So the story is similar for water. This is another nice summary plot, but also builds on a lot of other previous works. And so we're showing the water abundance with respect to H2 on the y-axis, and again, sort of evolutionary progression along the x-axis. And we see that in this case, by the protoplanetary disk stage, we're many, many orders of magnitude underabundant in water compared to what we would expect. So it's just a general theme then that oxygen seems to be missing from the gas by the time we get to the protoplanetary disk stage. So there is a really compelling explanation to kind of tell us why we're seeing this particular emission pattern. And the idea has to do with how the chemistry in the disk is coupled to the physical evolution of the disk. So in younger disks, we expect that we have small dust grains that are sort of vertically distributed throughout the disk. And these dust grains are coated in ice mantles of volatile molecules like water. So as the dust grains stick together and grow over the course of the disk lifetime, they settle to the midplane and they carry their volatile reservoirs with them. So this leads you to have a midplane that's very rich in things like water ice, but an atmosphere of your disk that's quite poor in oxygen. And a really interesting prediction of this framework is that we expect that actually pulling oxygen out of the gas should have a big effect on the chemistry of other chemical families as well. So this is a model by Fujian Du in 2015, showing how the column density of different molecules in the disk vary in sort of different physical conditions. So if we're looking radially, moving outward from the star, and the solid lines here are showing a case where the oxygen levels are sort of ISM-like, whereas the dashed lines are showing the case when you have oxygen depleted from the gas. And we see this orders of magnitude boost in the abundances of molecules that are part of the cyanide and hydrocarbon chemical families. So this is sort of a prediction that as we deplete oxygen from the gas, we're going to be reshuffling the chemistry of other sort of important elements as well. And sure enough, we can really confirm this observationally by looking at the emission of hydrocarbons and nitriles. So here I'm just showing examples of C2H and HCN. And there's loads of evidence accumulating that hydrocarbons and nitriles are surprisingly abundant in the surface layers of the disk, and that this likely corresponds to a very low oxygen content in the gas. So this is especially true in the case of C2H. Modeling is beginning to tell us that we actually really need very high abundances of carbon with respect to oxygen to reproduce this emission. So let's talk about the implications of this. What we've seen is that there's a large redistribution of oxygen between the atmosphere of these disks and the midplane. So we end up with an atmosphere that's very low in oxygen, but rich in the chemical families like cyanides and hydrocarbons. So what this is telling us is that carbon in the disk atmospheres is actually being removed from its dominant volatile carrier, which is typically CO, but it's being partitioned instead into families like cyanides and hydrocarbons. Another kind of important implication of this is that we expect that the planet-forming midplane should be very rich in oxygen-bearing ices. So we need this sort of water-rich midplane to explain where all the oxygen has gone from the gas. We also infer that the volatile chemistry is very tightly linked to physical processes like grain growth, and that the sort of interplay between physical and chemical evolution is going to be very important. And the last sort of takeaway that I just want people to kind of appreciate is that although we can't directly observe what's going on in the planet-forming midplane, we can actually get some really important insights into what's going on in this region based on observations of the chemistry in these elevated disk layers. So we see as evidence that the volatile chemistry is strongly linked to the disk physical evolution. So it becomes then really important to understand what timescales this evolution is taking place relative to planet formation. Are you forming your planets in this sort of water-rich midplane at later stages, or in perhaps a more kind of typical water environment earlier in the planet formation process? And so another real overhaul in our thinking that's happened recently is the idea that grain growth processes, which are really the first steps in the planet formation process, are happening much earlier than we previously expected. So there's evidence accumulating on a number of fronts that this grain growth is happening already in the protostellar disk stage. And I think that one of the most dramatic illustrations of this is the D-Sharp survey, which was an ALMA campaign led by Sean Andrews, looking at the dust in protoplanetary disks with extremely high spatial resolution. And what we see is that in almost every disk we look at, we have this really dramatic ringed substructure, kind of like I showed you before for HL tau. So there's a number of different explanations for what's actually causing these substructures, and planets is one of them. If you were to pop a planet in one of these gaps, it might sort of eat up all the material and carve out one of these rings. But whatever your favorite mechanism is, it's very clear that the dust has already undergone really significant evolution by the time we reach the protoplanetary disk stage. So by the time we're able to look at these objects, these processes seem to be well underway. So remember from earlier that protostellar disks offer a very different physical environment compared to protoplanetary disks. So we expect that the chemistry going on the small scales in protostars is going to be somewhat different from what's going on within the protoplanetary disk. I will say that observing protostellar chemistry has very different challenges compared to protoplanetary disk chemistry. In the case of the protoplanetary disk, all of our envelope is cleared and we're looking basically at isolated structures. But in the protostellar stage, the disks are on very small spatial scales, still embedded in the envelope and accompanied by these other features like outflows and shocks. So it can be really difficult to disentangle what actually the chemistry in the protostellar disk looks like. So this is something else that we're making progress in recently. So I want to just sort of walk you through how we might use different tracers to actually target these different protostellar components and try to really isolate the disk itself. So this is a protostellar disk candidate in the Serpens cloud. First thing I'm showing you is the millimeter dust emission. So we can see this really bright protostellar core where the disk is forming, but we also see this fluffier material that's probably just associated with the envelope. If you were to just look at CO, you would trace this really beautiful outflow from the protostellar core. And the red and blue contours are showing you emission that's moving away from us and towards us. So we can actually get some kinematic information as well, which will help us in sort of disentangling these pieces. If we look with a rarer CO isotopolog like C18O, we can actually pick up much more compact material that is actually rotating around the center of the protostellar source. So what we're seeing here is probably more associated with the protodisk itself. And another tracer, HC15N, is also really allowing us to zoom in on this compact rotating region, which is, again, where this protodisk is forming. And then lastly, we might have something like C2H, which really depends strongly on the presence of photons. And so this actually cannot form coincident with a dust disk in the protostellar stage because the envelope is blocking all the UV. We're only seeing C2H show up in the cavities carved by the outflows where you're actually exposing the gas to UV radiation. So I think it's really exciting that we're beginning to be able to pick out these sort of cartoon components of the protostar and actually see them mapped out onto real structures. I think we are in the early stages of characterizing the volatile chemistry in these protostellar disks. We're certainly much less far along in understanding the sort of bigger picture patterns than the understanding that we have in protoplanetary disks. But I think this is a growing area of research and is going to be a really important direction for the field moving forward as we sort of begin to isolate the exact timescales when planet formation processes are happening. Okay, so up until now, I've been focusing mainly on carbon, nitrogen, and oxygen chemistry. And that's for the very practical reason that the carriers of these elements are much easier to detect along the star formation sequence. So in contrast, the phosphorus and sulfur, the sort of missing pieces from this assembly, are generally in very low abundance in the gas phase. So we think that they're probably sequestered onto grains, which makes it a lot harder for us to characterize their chemistry. So just as a kind of quick overview of what we do know, sulfur, we're learning more and more about sulfur with higher sensitivity observations. So ALMA in particular is again allowing us to detect and map the emission of sulfur-bearing molecules. And we've seen it now in protostars as well as protoplanetary disks. So here's just an example from Maria Drozovskaya in 2018, showing this kind of diverse array of sulfur species that you can characterize in this protostellar source. And then last year, there was a really nice paper by Roman Legal looking at CS and H2CS in protoplanetary disks. And we see this really bright, beautiful emission of these molecules in the disk stage as well. In the case of phosphorus, though, our understanding is a lot less advanced. So phosphorus has only been detected towards 2 sun-like protostars. And we have not yet seen it towards any protoplanetary disks to date. So the sources where we have seen phosphorus, one is the source L1157. This is an optical image. It's not an ALMA map like you've been used to seeing, but just to sort of illustrate the structure of this source on large scales. So when people target the protostellar core itself looking for phosphorus, they don't find any emission there. But when you look a long ways away, 63 arcseconds away, in this B1 shock position, these authors in 2011 and 2016 were able to detect emission from PO and PN. So the other source where we found phosphorus, B1A, again, this is not a map of phosphorus emission. This is SIO that's sort of showing you, again, the nice outflow structure of this source. So in this case, we actually led an observation effort that detected PO and PN in the outflow of this source as well. So in this case, we're a lot closer to the protostellar core than in L1157, but it is still seeming to be quite associated with this outflow. So just in general, it seems like outflow shocks are really required to release phosphorus into the gas phase. We don't really identify it in more quiescent, unshocked regions. We also see that even in these regions where we can detect phosphorus, the abundances are extremely small. So we're talking a fraction of a percent with respect to the cosmic phosphorus abundance. Additionally, only PO and PN have been detected in star-forming regions to date. And so kind of in contrast to the sulfur chemistry, we have very few phosphorus carriers that seem to be in the gas phase. So this is a really nice result that came out earlier this year, actually, and it was the first map of phosphorus emission on the sky. So this is a high mass source that is not really a great analog for the formation of a star like our sun, but it still shows really clearly the sort of clumping of PN emission along outflow cavities. So these dashed lines are showing sort of the contours of the outflows that are traced by other molecules. And you can see the phosphorus emission in this sort of color scale here really seems to be associated with these outflow cavities. So I think this is exciting that we're beginning to be able to map this emission and learn something more about where the phosphorus is actually coming from and perhaps what form it's stored in the grain. So coming back to this picture, we see that these more volatile elements like carbon, hydrogen, nitrogen, and oxygen, as we study their chemistry along the star formation sequence, we see that they're partitioned in different molecules depending on the local physical conditions. In contrast, sulfur and phosphorus seem generally to be mostly locked up in grains. We don't know yet whether this is an ice phase or a refractory phase, but we do know that there's just a few percent or so of sulfur and phosphorus that's actually in a volatile form. So while sulfur in its volatile form exhibits this really rich gas phase chemistry that we can detect in both protostars and disks, phosphorus is almost exclusively found in these sort of energetic shocks in protostars, and it only shows up in the form of PO and PN. So I think a really interesting implication of this is that for these more volatile molecules, the inheritance might actually vary depending on the history of a given system, because we're really sensitive to the local physics. So if you have a star that's being born in a higher radiation field than another, that might really impact sort of the partitioning of these molecules as they are being incorporated into sort of planet-forming material. But in the case of sulfur and phosphorus, I think the inheritance may be more consistent between different systems, because if they're sort of sheltered in grains, they may be less sensitive to what's going on sort of in the physical environment. So just to sort of summarize what we can learn from these observations, we've seen that ALMA is revolutionizing our view of the chemistry and physics going on in protostars and protoplanetary disks, which are the precursors of planetary systems. We know now that planet formation may be going on in both of these stages, but the timing is still unclear. It is essential to understand how the chemical and physical evolution are coupled, because we think that the chemistry is going to be very dependent on the sort of local physical evolution. And so this could have strong implications for the material that is being incorporated into sort of protoplanets at different stages in the disk lifetime. So I think I've shown that while we can sort of indirectly infer the composition of volatile solids in the disk midplane, this is sort of an indirect science. So we would really like some complementary constraints to try to understand better what's actually happening to the ices in the planet forming region directly. Okay, so let's take a minute to think about what the chemistry of these icy volatiles actually looks like. So here's just a little cartoon of an ice mantle, and there's a number of different processes that we have to consider that regulate the chemistry. So accretion onto the dust grain and desorption off of the dust grain are basically going to set the sort of molecules that are available for reaction. We also have the ability for molecules to diffuse within the ice mantle and also to find reaction partners and react to form new molecules. We also know that photoprocesses are probably very important, and so you might have photons that are able to dissociate molecules within the ice or actually to desorb molecules off of the ice surface and into the gas phase again. So these microphysical processes in the ice are really mediating the chemistry, and this is what we want to understand if we want to try to sort of predict the outcomes of this ice phase chemistry. So one way that we can test these outcomes is using modeling. So in a sort of typical framework, you would take a chemical reaction network that describes all of the different players that you have within your kind of chemical scheme, and describes a lot of these different processes, both on the grain and also in the gas phase. You would then couple this with a physical model of the disk that describes basically the temperature, density, pressure, and kind of radiation environment in the disk. So this is just an example showing sort of the top half of a cross section through the disk. And so when you couple this chemical reaction network and the disk physical model, you can then sort of project how the chemistry is likely to play out over in sort of a more realistic environment. So I want to walk through a really nice example illustrating how you can actually use this kind of modeling to infer midplane compositions based on gas phase observations. And this is work that was done by Ryan Loomis in 2018. So in this paper, they had a really nice suite of ALMA observations of methyl cyanide. And in order to try to access the ice phase abundance of this molecule, they did this modeling framework where they started with the physical model of the disk describing the temperature and UV field and other sort of physical properties of the disk. They then coupled it with a chemical network, and the result of this model allows you to basically predict the distribution of gas phase methyl cyanide in the model. So here we see this sort of strip of where the model predicts that methyl cyanide is going to be formed efficiently in the disk. You can then compare your model predictions with the observed column density profile. So here, the blue line is showing the observed profile, and the red line is showing you the model that's been smoothed to kind of account for the observational effects of observing something with an interferometer. And then lastly, once your model and your observations are in good agreement, you can then predict the composition of molecules that you can't directly observe. So this is the distribution of ice phase methyl cyanide in the same disk model. And with this ice distribution mapped out, we can then start to make some really interesting comparisons. So here I'm showing a figure that has the methyl cyanide abundance on the y-axis, and they're also showing the cometary abundance of this molecule for reference. So cometary material is thought to preserve material from when our own solar system was in its disk stage, so it's sort of the natural comparison for these other protoplanetary disks. And so the x-axis is showing you basically a measure of elevation, where the left side is the midplane and the right side is the disk surface. And for different radial cuts from 10 to 30 AU, which is what we think is roughly the comet forming zone, we see a similar pattern, which is that the methyl cyanide abundance is lower than the cometary abundance in the disk midplane, but it's actually consistent with the cometary abundance at slightly higher elevations. So this is quite interesting because it's telling us that in this particular case, either we need for vertical mixing to be extremely effective such that the midplane population is actually basically kind of comparable to the abundances that we have at higher elevations, or our disk needs to have inherited some midplane material from the protostellar phase that will sort of boost this methyl cyanide abundance into better agreement. So with a modeling framework like this, we can actually begin to sort of address this question of interstellar inheritance and the role that chemistry in the disk versus chemistry in these previous evolutionary stages is playing. So I've just shown one example for how we can use disk chemistry modeling, but in general, it offers us a way to access the chemistry that we can't observe directly. So this is really powerful. But the caveat here is that our models are only as good as the physical and chemical inputs. So we want really good constraints on the fundamental microphysical processes in order to be able to confidently interpret the results from our models. So for this, we can use laboratory experiments. And this is a large part of what I did for my PhD, actually. So this is the vacuum chamber that I worked on while I was a PhD student. It's an ultra high vacuum instrument, so we can reach pressures that are about 13 orders of magnitude below atmospheric pressure. And it's a cryogenic system, so we go down to temperatures as low as about 10 Kelvin. So as a sort of schematic of the instruments that we use to study this ice chemistry, this is the outline of our vacuum chamber. And this helium cryostat is cooling this window down to very low temperatures. So we can release whatever gases we're interested in studying into the chamber. They condense onto this cold window and form an ice layer. We can then study the chemistry in situ using infrared spectroscopy to measure the composition of the ice that we've deposited. And then we can also use quadrupole mass spectrometer to measure the composition of the gas in the chamber. And if we happen to need some sort of energy source, we can use a UV lamp or an electron gun or some other sort of energetic processing. So the questions that we would like to answer are what kinds of chemistry are active under these cold midplane-like conditions, and how important do we think chemistry in this sort of sheltered midplane of the disk is in reshaping material between the sort of interstellar stages of star formation and the ultimate kind of accretion of planetary bodies. So I'm gonna just walk through one example, which is the characterizing the formation of ammonium salts in ice. So astronomers, salts are ion pairs. So this work was motivated by the observation that when we look at ice absorption spectra in protostellar lines of sight, we see actually that ions like formate, OCN-, and ammonium are actually kind of common constituents of interstellar ices. So the way this works is we're basically using the star as a backlight to observe the kind of icy material that's absorbing light along the line of sight to our telescope. And it's a little bit surprising that we actually see these ions that are frozen into the ice phase. So we wanted to see if we could generate these salt pairs through ice phase chemistry. And the system that I was looking at is the reactions between ammonia and formic acid to form the ammonium formate salt. So the way we do these experiments, we deposit a layer of ammonia underneath a layer of formic acid on our cold window. And then we can characterize the chemistry using infrared spectroscopy. So here on the bottom, you're looking at the sort of individual constituents, ammonia and formic acid. And then the sequence of temperature spectra is showing you how the infrared features change as you're warming a mixture of ammonia and formic acid. And we basically see the formation of these new features that correspond to these ion pairs. So ultimately, we really like to understand the energetics of this salt formation. And so to do this, we measure the kinetics. So this is a time lapse of how the infrared absorbance changes over the course of an experiment. And from this, we can derive a growth curve. So in order to derive the kinetics, we then fit our growth curve with a kinetic model, and we can actually use different models to tell us something about the mechanisms by which this chemistry is happening. So in this case, we see that a two-step model fits the data really nicely, while a single-step model is not really as good of a match. So it's just telling us that this chemistry is proceeding in two distinct steps. And so for each growth curve, we then get out these two different reaction rate constants from these sort of two different steps of the process. And when we run this experiment at multiple different temperatures, we can basically constrain the reaction energy barrier by seeing how the rate constant depends on the temperature. So in this case, we see that this is a two-step process that has these two different energy barriers. And what we think these correspond to are a pre-reaction step that describes the sort of dynamics of the ice. So a molecule reorienting or diffusing in order to react. And then there's an actual reaction step, which is the chemical barrier to proton transfer. And based on our experiments, we see that the activation barrier of the reaction step is quite low. So this should be possible basically at any temperature you're looking at in the interstellar medium. But the reaction barrier of this dynamical step is quite a bit higher. So we're only going to be active at somewhat warmer temperatures if we want this diffusion limited chemistry to happen. So that's not to say that it won't occur anywhere. It can still proceed in lukewarm environments that are around 30 Kelvin or warmer, but this is probably not happening in sort of the coldest region of your disk midplane. Now, a really interesting feature of these ice phase salt pairs is that they're a lot less volatile than their neutral counterparts. So here we're showing a temperature ramp as we warm the sample from 50 to 300 Kelvin. We can see the molecules come off of the sample into the gas phase. And we see that the neutral molecules come off at much lower temperatures compared to the salt. So this is pretty cool because it actually means that if we're forming these salts, then we might actually be able to retain nitrogen in the solid phase well past where ammonia would normally sublimate. And what was really exciting actually is that these ammonium salts were recently identified in the dust on Comet 67P by the Rosetta mission. So this was an orbiter that visited this comet out in space and was able to do a bunch of characterization. And among them, you see this reflectance spectra of the comet. And this is a lab spectrum of ammonium formate salts and some other sort of dust grain components, but we see that it's a really nice fit to the data. And so these authors have inferred that these ammonium salts may actually represent a really large fraction of the nitrogen reservoir in comets. So I think it's really exciting that this salt formation can increase the partitioning of nitrogen in the refractory phase relative to the volatile phase. And it's also really interesting because this sort of implies that the cometary material, at least part of it, likely experienced these lukewarm temperatures at some point in its history in order for this diffusion limited chemistry to actually be active. So just to sort of summarize, we've seen that these lab experiments can allow us to interpret and predict the ice chemistry that went on in our own solar nebula and that's actively going on in other disk systems. So we expect that most chemistry will be diffusion limited in the very coldest regions. But this can actually tell us something if we identify the products of this sort of diffusion limited chemistry in relics of our own early solar system. So coming back to this big picture, I think I've shown how we can use these different modes to basically together assemble a more complete understanding of what's going on in the planet forming disk midplane. So observationally, we gain indirect insights into the partitioning of volatiles between the gas phase and the solids. And we can also learn a lot about the physical environment that this planet formation is happening in. In the lab, we can use experiments to make robust measurements of the ice microphysics and the chemistry and make good predictions for how this will actually play out in sort of interstellar-like conditions. And lastly, we can use astrochemistry models to map between these two and to make predictions about the compositions of midplane ices that we can't observe directly. So going forward, there's a lot of really exciting directions that I think are going to be on the horizon. But what I'm most excited about is the ability to actually measure ices in these protoplanetary disks. So we can do this with infrared telescopes, again, using this sort of line of sight absorption spectroscopy. And this was done already by a number of space-based instruments in the past. So here we're showing an absorption spectrum, and you can see this water and CO2 and CO feature. But these sort of previous generation instruments were pretty low signal to noise and much lower spatial and spectral resolution. So with the launch of the James Webb Space Telescope, coming in about a year from now, we're going to have huge improvements in the sensitivity and spectral resolution and get much better constraints on the ice compositions in disks. So we'll be able to answer questions like, what are the abundances of the main volatile carriers and how important are simple versus complex organics? Are the ices mixed or layered, and what are the implications for their thermal history? And how do ice inventories evolve in the evolution from protostars to protoplanetary disks? So with that, I will just leave my summary up, and I'm happy to start the discussion.
Great. Thanks very much, Jenny. That was great. Really enjoyed it. Very informative, really exciting. So I'd like to offer, people can put their questions into the Q&A down below, and we'll pass those on to Jenny. While you are starting to do that, let me introduce the other member of our panel that's going to sort of lead our discussion here. That's Takeshi Oka. Takeshi is the Robert A. Millikan Distinguished Service Professor in Chemistry and in Astronomy and Astrophysics. He's very well known for his work on H3+ cation, which is the critical precursor to the formation of all sorts of larger molecules. Some similarity to what Jenny just said. He both characterized it in the lab and was the co-discoverer of it in interstellar clouds. So why don't I start by asking kind of the first question that popped to my mind. I'm coming from my spectroscopy background, Jenny. As you were talking about radio emission, the first thing that came to mind is, what are you biased in your observations in some way by the types of molecules that you observe? And I guess I was coming at this from different points of view. One of them was, I think wouldn't you need polar molecules in order to see them? And then the related question is there a certain mass range of molecules that you can or can't see?
Yeah, definitely. So like you said, we need a permanent dipole to be able to see things with radio telescopes. And so this rules out directly detecting things like O2 or N2. And so that's kind of particularly problematic for N2. We still don't really have a good understanding of how important N2 versus other nitrogen carriers are. So that's definitely a limitation. And the size of the molecule is as well. So as your molecule gets bigger, the intrinsic line strength of the different lines that you can observe becomes weaker. And so we just have a much harder time characterizing the emission of larger molecules. So that's part of why it was really exciting to kind of finally be able to detect these larger organics in disks, but there's still only 6 atoms. So I think that we are then much more dependent on modeling to predict the composition or the abundances of even larger molecules. I see.
Does that have anything to do with why it's so hard to see anything with phosphorus that's bigger than a diatomic?
I think that in that case, it's just that phosphorus doesn't really want to be in the gas phase. Okay. So I mean, we see sulfur in a number of different forms. So I think that phosphorus must just really be locked up in some more refractory species. Okay. I'm going to ask a question from the audience and then hand this over to Oka. Question from Michelle Brandt. For the diffusion rate constant, how does that relate to the thickness of the ice films? So it doesn't matter as much the thickness as the composition. So we should be able to describe a diffusion rate constant that sort of just describes how far your molecule can go as a function of time. So if you have a thicker ice, it'll just take longer for things to diffuse. But the composition is really important. So the particular experiment I was showing was was not that realistic for an interstellar ice because we don't often have pure ammonia formic acid ices in the ISM. So in a water-based ice, the diffusion would probably have somewhat different energetics, but it's probably kind of a comparable order of magnitude at least.
Thanks. Oka, do you have any questions for Jenny?
Yes. Can you hear me?
You're loud and clear.
Okay. Oh, do you see me? Yeah.
Yes, I see you also.
Okay, okay. Jenny, thank you very much for this very interesting talk. I learned a lot about the protoplanetary protoplanetary disk chemistry. And I would like to know more about the general picture of the chemistry of protoplanetary disk. I remember very soon after the turn of the century, there was a surprising paper appeared in Nature with fanfare that there is a lot of gas in protoplanetary disk, and in particular, molecular hydrogen is 1,000 times higher than previously reported. I was really surprised because that I thought was very unlikely, but I don't know the current consensus on this problem. Do you, what is the consensus now about the hydrogen, molecular hydrogen abundance in protoplanetary disk?
Yeah, so I definitely haven't heard much about the hydrogen abundance being higher than in previous stages. I think that it is hard for us to measure the masses of disks because our main tracer CO is much less abundant than normal. And when you're using dust emission to make that conversion, then we're dependent on assumptions about the dust to gas ratio, which we also aren't super sure about in the disk stage. So I think our constraints on disk masses aren't good, but I don't think that most people consider that the hydrogen abundance is higher.
Do you have any idea, or is there any consensus about the hydrogen-carbon ratio, which is interstellar space, it's 4 orders of magnitude difference, but in protoplanetary disk, it must be lower, right?
Sorry, the carbon to hydrogen ratio?
Carbon to hydrogen ratio.
Yeah, so I think it depends on what part of the disk you're looking in, because we do see some sort of vertical repartitioning that probably affects carbon, but I think the gas is probably has a lower carbon abundance than the interstellar medium.
Yeah.
Because carbon is also
how much lower?
I think it can be orders of magnitude, but this is a number that I think varies a lot depending on the particular model that you're using. So yeah, I think orders of magnitude is definitely on the table.
Actually, if you reach planets, then the current solar system, then it's almost, hydrogen is almost gone, right? It is condensed in Jupiter perhaps, but interstellar hydrogen is almost completely gone. Mm-hmm. The protoplanetary disk is a step towards that picture, and I was just wondering if there is a consensus in your field, but if not, that's fine. I have one more question. In your talk, I found the most interesting part I found was a nitrogen-oxygen ratio. And I thought you said that oxygen in gas phase is depleted. Is that the reason why nitrogen abundance is so much higher than oxygen? Or
yeah, so the oxygen we think is very depleted from the gas, and this basically frees up sort of more carbon to react with nitrogen. So you tend to see more things like cyanides. But again, we can't directly detect N2. So I think we're a bit limited in our understanding of the total nitrogen budget of the gas. It's just that we see more of the cyanides compared to previous stages.
Well, what I found most interesting was that the phosphorus compound, the phosphorus oxide abundance is comparable to phosphorus nitride, right? That I found that's very, very surprising.
Yeah.
But does that show that phosphorus oxide is produced in gas phase? Or does that mean anything? Does that indicate anything whether these two compounds are produced in gas phase or grain?
Yeah, so the phosphorus chemistry is really poorly understood, and a lot of the networks now assume that you basically make phosphine on the surface of grains. Phosphine is desorbed, and then it's gas phase chemistry that produces PO and PN. But I don't think that that's well proven necessarily. So one of the weird things is that in all of the star forming regions where we've detected PO and PN, the ratio between them is almost constant in very physically different environments. So to me, that seems more like what we're seeing might be a closer relative of what's stored in the grain, the fact that we have this very consistent ratio. But I think the chemical networks have just not fully explored the phosphorus grain surface chemistry.
Okay.
You don't mind?
I have many more questions, but probably I should stop here. I'll ask you privately.
Thanks, Oka. You have to stick around afterwards. We've still got questions from our audience. Actually, let me stick on the phosphorus subject. Doretta Miller asks, where on Earth is phosphorus found? Near deep underwater vents? How rare is it on Earth?
So I think that phosphorus is often in mineral form on Earth. So it is sort of associated with more refractory material. Volatile phosphorus is obviously sort of a component of biochemistry. But I'm not totally sure as to the sort of distribution in different like deep sea vents versus other places on Earth. So I'm definitely not the expert to answer that question.
I suspect it's very abundant, but I have absolutely, like you, got no idea how, when, where. Let's see, another question. This one from Yoav Kashim. If I remember correctly, early in the talk, you said that meteorites may have brought important bonds for life to Earth. Why do you focus on bonds rather than elements? And I suppose bonds refers to molecules, I guess.
Yeah, so I think that's part of the discussion of if you can deliver a molecule intact, or at least sort of preserve, for instance, like a peptide bond in the delivery, you might have a leg up in subsequent prebiotic chemistry, as opposed to if you have to then kind of do the synthesis fully in a terrestrial environment, that could be challenging. So I think, like I said before, I don't think that we should really weigh in yet on which form we need to have the delivery take place in. I think it's sort of interesting to explore both options, but that would be the benefit if survival is efficient, that you could sort of jumpstart the chemistry perhaps a little bit more easily.
Great, thanks. I'd like to go back to one of my own questions, if you don't mind. It really kind of stunned me a little bit that you see emission from dust grains. I mean, is that really literally the case that you're seeing thermal emissions from a macroscopic object? But
Yes.
Is there a way I should think about why this is just black body radiation? Is that basically?
Yeah,
it?
exactly. So the dust absorbs really efficiently at usually shorter wavelengths and then re-radiates at longer wavelengths. So we're basically just detecting the black body emission from these sort of millimeter-sized dust grains.
Very not intuitive to me, but
Yeah.
thanks. And the other, question I had was about, sort of the missing oxygen. Can you just sort of summarize what are possible, if oxygen's hard to find, what are the possible molecular sinks, or maybe it's atomic, sinks for oxygen? Where, where could it have gone, basically? And
Yeah. So,
go ahead.
Oh, this is a very active area of research trying to figure out how you can actually trap the oxygen in a form that it can't get back into the gas phase. So I think that this sort of physical separation is really important, where it's overabundant in the midplane and underabundant in the atmosphere of the disk. And then the question is, how do you actually keep it trapped in the midplane? So you can put it in something like water that is a lot less volatile, or you could kind of convert it to oxygen-bearing organic molecules that are less volatile. And there's also the idea that as you're sort of building up your dust grains, you're incorporating a lot of that icy material into them. And so you're basically then kind of physically trapping the ice in addition to kind of chemically trapping it. So it's probably some combination of these physical and chemical processes.
If just sort of stepping back a little bit, in your field, and broadly speaking, are there one or two sort of grand challenges in the business, or that you could tell us about? Or maybe the other way to say it is, if there was one particularly important piece of information that you wish you knew, what would it be?
Yeah, so I think, in a very achievable one is the one that James Webb will give us. So actually having direct constraints on the ices and disks, I think, is going to be game changing for us. We'll actually be able to see what the role of these larger organics is, and see sort of things about the thermal history that the material experienced during its journey to the disk. So I think that having those direct constraints on the midplane composition is going to really help us to kind of make sure that everything we've been thinking so far actually fits with the reality.
Then maybe, maybe even a step further back. I mean, just what's your personal perspective on how this research you've told us about, how it sort of fits into the broader area of origins of life research? To me, it seems like it's a very early stage, but what's your perspective on this?
Yeah, so I think we definitely we need, I think, a better understanding of how material is actually incorporated into the processes of grain growth. Right now, we can sort of associate things radially in the regions where we think comets are forming, and maybe even at the same time that it's happening, but we can't really see sort of how destructive of a process grain growth is. And I think it's pretty well established that when you're forming a rocky planet, it's not likely that that volatile, the sort of primordial atmosphere is going to survive. And so I think there is a role for this kind of later stage delivery from icy bodies like meteorites or comets. But yeah, I think putting the pieces together of how exactly or where exactly the volatile reservoir that we need to be interested in is, and how the processes of grain growth are going to perhaps alter the chemistry that we can observe, I think are important areas.
Sorry, just to follow up on that for a moment. I didn't follow that. Is you said you think that a lot of the small organics might not actually sort of survive the planetary formation phase? Is that, did I hear that correctly?
So it depends where. If you're talking about a terrestrial planet that is forming very close to the star, like where at the region in the disk where Earth formed, it was too warm for most kind of volatile molecules to be in the solids. And so we sort of accreted our original atmosphere, but then there was also sort of later stage delivery of volatile molecules that sort of repopulated the atmosphere with more perhaps interesting molecules. So, so depending where the rocky body is forming, it may or may not actually kind of hold on to this volatile reservoir.
Good. Olga, do you have any further questions? I guess you have lots, right? If you have another one.
Maybe I'll tell you just one more thing. We know that water is produced in gas phase very easily, whereas we cannot produce ammonia in gas phase. Ammonia, there's no way to produce ammonia in gas phase. So I'm a bit surprised that oxygen is depleted more than nitrogen in gas phase. That was a kind of general question, which ammonia cannot be produced in gas phase, right? That is one of the main reasons that solid state chemistry was introduced. And so it's so much easier to make water in the gas phase, whereas making ammonia in gas phase is impossible. That's because of nitrogen proton affinity is lower than the molecular hydrogen proton affinity. So the normal channel of protonating molecules and producing molecules just doesn't occur for ammonia. It occurs very well for carbon compound and oxygen compound, but not for nitrogen compound. So that makes me even more surprising that oxide versus nitride concentration is so much higher than the oxide concentration, in spite of the natural abundance, a huge factor between oxygen and nitrogen. Anyway, this is a general question, and probably no quick answer is available, but I just raised that one.
Yeah, so I think a lot of the nitrogen chemistry in the disk atmosphere is being kicked off not through ammonia, but starting with N2 or atomic nitrogen. And so it's just a different pathway that is kind of forming these molecules compared to how you would form ammonia.
I've got another question that's come in. Jenny, how much variation do we see from one star to the other? I mean, do we see similar evolution paths, or is each system, distinct, have its own path?
Yeah, there's definitely a diversity of physical environments from star forming region to star forming region. A lot of it depends on whether you have massive stars nearby, then the sort of radiation field is a lot higher in a disk nearby in that context. So that's, yeah, just one example, but also depending on various things like how big is the star that you're forming, that can have a huge effect on the physics in the disk. So there is quite a bit of variety that we see.
It's just curious, follow up on that. Is photochemistry really a requirement in all of the scenarios you look at some point in the process?
At least in the surface layers of the disk, photochemistry is really the main driver. I think in the more shielded, like mid-plane regions, it may have less of an important role, but yeah, photochemistry is really the thing I think that makes disks look so different from the other stages of star formation.
I'm afraid we're running out of time. So what that means is I'm going to have to sort of wrap things up here with, of course, the question we always ask everybody, and that is, given what whether it's what you discussed today or otherwise, what are your thoughts on life existing beyond planet Earth?
Yeah, I feel good about it. I think that it's pretty likely just based on.
It's good life, not evil life. Is that what you mean?
Oh, I can't comment on that yet. But no, I think the likelihood is high. Planet formation is such a common outcome of star formation, and we see so many of the right ingredients in these other systems. So to me, it would be very surprising just statistically if you didn't have it happen in other places. But.
Okay, that's really great. With that, Jenny, I'd like to thank you very much for that talk. Really learned a lot. Very exciting. Thank you. And I'd also just sort of like take the opportunity to advertise to the audience to stick with us, please, and come back at this point next week. And let's see, next week, I guess we've got Dan Clavin. We'll be talking about meteorite delivery. So with that, we'll sign off now. Thanks very much, Jenny.
Thanks, guys.